Jeff is one of my most valued colleagues since we conducted research at Clear Lake here in the state on mercury contamination. But he's a professor of water resources and environmental engineering at UC Davis and the founding director of the Tahoe Environmental Research Center, TERC. TERC conducts critical scientific research underpinning the restoration of Lake Tahoe and other bodies of water around the world. For over 30 years, Jeff's research has focused on the interactions between complex fluid motions found in nature and their impacts on water quality, environmental health, and watershed processes. UC Davis researchers have been monitoring Lake Tahoe for the last many decades, since the 1960s, and that data has shown a significant decline in the clarity of Lake Tahoe. From the year 2000 to 2020, despite huge financial expenditures and research efforts, the clarity did not improve. So out the window with all that money. However, for some unknown reason, starting in August 2022, Lake Tahoe's clarity suddenly improved to levels not seen in over 50 years. So it's pretty remarkable. Today, Professor Schladow will delve into the potential reasons for this shift in his presentation with the provocative title, The End of Lake Tahoe as We Know It. So with that, Jeff, I'm sure we're all waiting with bated breath to hear all about it.
Well, thank you, Tom. So I actually started at UC Davis in 1993, and as any assistant professor starting anywhere knows, it's always hard to get that first money to start the research you want to do. I'm not missing much. But anyway, it was Tom and his colleague Pete Richardson who happened to walk into my office one day to say, we have some money if you're interested in doing something up at Clear Lake. And so I guess that was 1994, I think. And well, I'm still working on Clear Lake. Tom was smart enough to move on. Actually, I love Clear Lake. Okay, so this is a provocative title, deliberately, The End of Lake Tahoe as We Know It. Tahoe has existed for about 2 million years. So it makes it even more provocative that, and I guess, to think that we sitting here can end it right now after 2 million years. But that 2 million years, 1,985,000 of those years was without humans, which was a good thing. And something like 1,999,823 was when Europeans were there. So that was the year that John Fremont just stumbled over, I guess, what's now known as Carson Pass. His guide was Kit Carson, and was the first European supposedly to see Tahoe. So during that time, during those 2 million years, the lake has already changed. It's changed dramatically. It's a lot deeper. And because of the way Lake Tahoe was formed, it's a graben lake. It was formed by earthquake faulting, and every so many thousand years, it would deepen and deepen and deepen. The location of its outflow, you all may know that it flows out from the northwest at Tahoe City. It used to flow out from the northeast, but volcanic activity hundreds of thousands of years ago changed that. There have been tsunamis on the lake as a result of underwater landslides that produced 100-meter, 330-foot waves across the lake. So all these things have changed. I'm not talking about the end of Tahoe on account of those sorts of cataclysmic events. I'm talking about Tahoe as it is now, maybe as it was when you first went there, as a graduate student, like I did, or with your parents or grandparents or something like that. So more contemporary changes. And the changes that I'm thinking about aren't all bad. I mean, it's Friday. It's been a terrible century. So yeah, why ruin the rest of it for you? Okay. Oh, that's the wrong computer. Sorry. Oh. Okay, so just to orient you, this is on the right, that's sort of North Lake Tahoe, but it's on the left where I want to draw attention. This is something I just cut out of UC Davis's homepage. And I read when I first came across this, I thought it was great. So the big blue pin is UC Davis, and to the left there's Bodega Marine Lab and the UC Davis Health System, and Tahoe is there. Our lab is there. So we actually, I guess we're the smallest of all those pins as in our physical size, but it's really important. And well, our main laboratory there is located in Incline Village, Nevada. So you may feel free to call me the Chancellor of UC Nevada. Whoops. Work out how to use this. Okay, well, no. Okay, so 2022 and 2023 were arguably the most extreme. Yeah, could you get rid of? Oh, no. Well, 2022 and 23 were arguably the most extreme years for Lake Tahoe, but not from the traditional climate change perspective. So this is the traditional climate perspective. I love this data when I came across it. So this is showing air temperature data averaged across the whole globe, pole to pole, all the way around. Each of the squiggly lines represent different years. And the one in black is 2023. And you can see on the 4th of July, it was the hottest day on Earth in 100,000 years. And it probably, well, I'm not sure, maybe, a week later, it got hotter. I doubt it. But overall, I think on track. I was just reading yesterday, this is on track to be the hottest year ever. So that's the climate change. It's okay. I got it. Surprisingly, though, despite all this, and Tahoe has experienced lots of climate change impacts, it's been relatively cool there. So I just got to do a little bit of internal. Shoot. Okay, well, how do I go back? I want to go backwards. Okay. So I'm sorry about that. Okay. So this is a strange figure. What this vertical axis shows is the depth to which Lake Tahoe mixes every year. So this, we'll say these 3 bars show that in 1973, 4, and 5, in winter, the lake mixed all the way to the bottom, it says 1,400 feet there. It's about 1,600 feet. But there are some years when it doesn't. Okay. And this has been one of the big mysteries of Lake Tahoe. Why does it mix all the way to the bottom some years and not others? So here we are at the hottest year ever, at least in a few 100,000 years. And it mixed all the way to the bottom. And the reason for that is that it was cool. It's as simple as that. Just because we're in a time of warming temperatures and climate change, we're also in a time of extremes. And so we're going to get some of the coldest years ever. So again, this is probably the most nerdy slide. But I felt I'm an engineering professor. I could get away without equations, but I have to have a graph or two. So each of these are the months of the year, and what the colored bars show are different years. So the blues represent 2020, 21, and 22. The orange is sort of the average since 1910, over 100 years of data. So November was really cold compared to old time. December was cold as well. November 2022 was the third coldest year. So it may seem obvious. And once we sort of saw it, it was kind of obvious. But the thing that controls whether the lake mixes to the bottom every year is whether there just happens to be a couple of cold weeks or a couple of windy weeks where the wind drives a loss of heat from the surface of the lakes. And next slide. So let me sort of explain this with, I guess, some cartoons of what happens to Lake Tahoe through the season. So those of you who go up to Tahoe, I mean, it's not the warmest place to swim, but it's not bad in the middle of summer. So in the middle of summer, this is a cross section of the lake. It might be 73 degrees at the top, 42 degrees way down here, 1,600 feet down. And at the surface, it's all mixed up because of wind and waves. And down through there, that color gradation represents what we call stratification, progressively getting colder and colder, progressively getting denser and denser. Next slide. So as we go into the fall, surface is cool, and that surface layer goes down. Next slide. And down. And usually in most winters, it kind of stops there. You know, winter, it lasts for 3, 4, 5 months, and it never mixes, it never breaks through and goes all the way to the bottom. Next slide. This year it did. It went all the way to the bottom, I guess, in late February 2023. So it totally mixed. The temperature at the surface was 41.3. At the bottom, it was the same. Next. An indication of just how cold it was is Emerald Bay froze. So I don't know, has anybody ever seen Emerald Bay frozen before? Yeah, I haven't found anybody who has. I've seen parts of it and parts of some marinas with ice on them, but never the entirety of Emerald Bay. Lake Tahoe will never freeze, he says. It's just too deep. There's just too much thermal mass there, and winter will hopefully never be that long to lose all that heat. Okay, next. Okay, so is this a good thing or a bad thing, all this mixing? Well, mixing sounds turbulent and crazy. We all like stability and peace. Actually, it is good. Okay, so yes, I apologize. This is nerdier than the previous slide. But I like this. So this is what I do. A lot of what I'm forced to do are talking about other people's work and what they're doing. This is something I've been doing, and actually I should give credit to my PhD student, Mika Swan. Okay, so I'll walk you through this. If you're used to seeing these sorts of figures, you know what it is. If you're not, it looks like something left over after a Grateful Dead concert. So this is the time axis on the bottom. So that's from January 1st, and it goes through to the end of April. And these colors represent the temperatures of the lake over time and with depth. So depth on the vertical axis. So up there at the top near that little letter A, the colors are orange. So the water there is about 8.5 degrees. 6.5 degrees. And you see, as you go down, it gets cooler and cooler, bluer and bluer. And as we sort of move through time, we see eventually it reaches a point here around early March where it's the same color top to bottom. That's the point I was talking about before, where it's mixed top to bottom. So something else I want to point out, these white lines, you can see there, they're lines of constant temperatures. So I'm not sure what the actual, excuse me, what the actual temperature is, but let's say that bottom one is at 5.1 degrees Celsius line of constant temperature. So you would think this big lake, so deep down, that that line of constant temperature would be constant. It would just be flat. But it's not. It's wiggling. And every time it wiggles, what that indicates is water moving vertically. So we call these internal waves. They bore the crap out of most people. But people like me, we love them. So these are not like waves you'd see on the surface of the lake. These are, if you look at the amplitude of those white wiggles and compare it with this vertical scale, it's like 100 meters, 300 feet. So inside this lake, water is slowly moving up and down. Now, it's not like we're having eruptions of water everywhere, because when it moves up in one place, it's moving down in another. So the surface stays constant. But all these motions indicate lots of mixing and turbulence, the things that help a lake. So what I have down here, if we look at the black, this is the temperature at the bottom of the lake. So we have instruments at the bottom. It's pretty constant, little few wiggles at about, say, 5.2. And right at this time, it starts very quickly going down. And so in a matter of 2 weeks, it's cooled. At the same time, the blue line, this is oxygen at the bottom, that jumps. So because of this mixing, because of this turnover, we've brought oxygen down to the bottom of the lake. If that didn't happen occasionally, then oxygen would start to diminish. So it's gone from whatever this is, 8 degrees to almost, 8 milligrams per liter to almost 9. We've sort of estimated, based on a lot of this data, that it would take about 20 or 30 years of non-mixing for the oxygen at the bottom to reach a point where it would start to get serious. Serious meaning certain organisms, say the trout, wouldn't be able to live at the bottom. They'd have to go higher. But even worse, the chemistry at the bottom of the lake would change, and you'd start getting nutrients coming out of the sediments, and the billions of dollars that Tom alluded to in the introduction that have been spent on Tahoe, much of which is being directed at controlling nutrients coming in, would be undone by nutrients just coming out chemically from the bottom of the lake. So that's a really scary prospect. The end of Lake Tahoe as we know it, except this work we've done indicates that there really has been, when we statistically analyze this data, there has been no climate change impact on the frequency of the mixing. We were expecting, we've been saying for years, climate change is going to cause mixing to slow down and stop. But this year, when we finally went through all the data, there's no evidence that that's happening yet. Next slide. Oh, okay. Everybody loves to go to the beach at Tahoe. I bet the last time you went there, it didn't look like this. Yeah. This is like the best advertisement for Hawaii. So this is, we call this Conservancy Beach. This is at South Lake Tahoe. This is the beach just to the east of Tahoe Keys. So it's open, it's sort of open land. It used to be part of the marsh where the Tahoe Keys are built. This was, I guess, late September 2022. This was before last year's huge winter. The lake level was low. What you're seeing here are algae, different forms of algae. It's very shallow water. Some of this stuff that's red there, that's probably iron-reducing bacteria. But this was horrible. It stank. There were flies. It's not Lake Tahoe as we know it. And this has been happening increasingly. Next slide. So these nearshore algae. So these are different than, say, phytoplankton out in the middle of the lake that are these microscopic free-floating organisms. So these nearshore algae at Tahoe come in basically two flavors. One is called periphyton, and these have to attach to something, to a rock or a pier, something hard, and they grow as these little stalks. They're sort of, I mean, some of them get as long as your small finger, and they grow and they're slimy and they're pretty horrible. Even more horrible is metaphyton. So metaphyton, they're filamentous algae. So they're actually made up of individual microscopic phytoplankton, but they form long strands. But they don't have to attach to a rock. And these are the ones that have been causing a lot of most of the trouble. Next slide. So this is an aerial view. This is somewhere on the west shore. I think that's Ward Creek, just coming in there. So one of the things we've been doing, I'll talk a little more about it later, is the way we used to monitor the algae on the shore is to go out to about 20 or 12 or 20 different sites around the shore, and scuba divers would go there. They would scrape the algae off, a certain area of the rock. They'd take it back to the lab. They'd analyze it for the biomass and the chlorophyll and all those good things. And they did this for about 25 years. And what they found at the end of that time is that pretty much nothing had changed. Well, you say, well, that's good. But over those 25 years, people had been complaining more and more, saying it's getting worse. I remember it wasn't like this, but the data said nothing's changed. So the conclusion we came to was that at any individual location, things hadn't really changed. But what was changing was the aerial distribution of it. It was taking up more, it was covering more and more of the shoreline. So what we did was we've started a program, this is the last 2 years, of not focusing on individual points, but trying to capture the condition of the entire shoreline. So one way we do that is we have a helicopter. Well, we don't have a helicopter. Even the chancellor of UC Nevada doesn't get his own helicopter. But a person who supports our program has one. And every month we attach cameras to it, and we fly around the shoreline, and we photograph every inch of the shoreline. And then we have drones. And so again, we go to certain specific locations to get higher resolution data. So this is a helicopter image, and you can actually see that banding, that striation, different colors. That actually represents different kinds of periphyton. So the brown ones near the shore, they're more of these stalk diatoms, the ones sort of like a little finger. And as you go deeper and deeper, you get filamentous green algae, and then you get actually, blue-green algae. Next slide. So this is an example of these helicopter images. So each of these little boxes is an individual image. They're pretty much stitched together in real time. So as the helicopter's flying, it's taking the imagery, and through software, they're producing a continuous map. So this is an example of the continuous map or continuous image built up from multiple images on the right there. And what you're seeing, this is the outlet of the Truckee River from Lake Tahoe. So that's Tahoe City you're seeing, and where the arrow is, that's the Truckee River, and the dam and Fanny Bridge are just downstream of that. And all that brown area is this periphyton. Tahoe City has always been bad because there's a lot of development there, but this is talking to people who have been going there longer than I have. It's never been that bad. Next slide. Okay, so if that's bad, this is the metaphyton. This is the other one. And then, again, this is the South Shore. This is Kiva Beach. That's a little bit west of Tahoe Keys. This is one of the I guess, Forest Service beaches there. So normally it's beautiful golden sand. And this is what it was in August 2022. And it's just slime, because it gets washed up on the shore, consumes oxygen, it stinks and flies, and it's terrible. And this was something we never used to get. The attached algae, yeah, people were seeing it 30, 40 years ago, not as much as now. This is totally new in the last 15 or 20 years. Next slide. Okay, and start. So here's a video. This is scuba diving in Lake Tahoe. And you start to see little bits of green there. That's metaphyton. And as you're swimming along, you're going to start seeing more and more of it. But where it really gets dense, you'll start to see little shells, little white shells on the surface of the sand. Okay, those shells are the shells of Asian clams. So this is an invasive species introduced to Tahoe somehow in about 20 years ago. So it's not quagga mussels, which is caused, or zebra mussels that continue to cause challenges in the Great Lakes and lots of other places. So these are clams. They don't attach to anything. They burrow down in the sand. But what they do when they burrow down in the sand is they have little siphons and they suck. That's their whole purpose in life, is to suck. They suck in water. They extract they filter out algae, extract the nutrients or some fraction of the nutrients, and then expel the remainder. So basically, they're using about 20% of what they extract for their growth, and then the rest is expelled. But in the process, they're concentrating it. And suddenly you go from the very low concentrations of nutrients you have in Tahoe to concentrations that are 10 or 20 times higher, which is what the metaphyton like. So they weren't introduced, they were always there, but it was always the concentrations of nutrients were too low to let them be a nuisance. Now they're a nuisance because the Asian clams are literally providing them with the conditions they need. Okay, next slide. All right, microplastics. This has been in the news lately everywhere. And it isn't something that microplastics were just put into lakes and oceans this year or last year. They've been there all along, but people haven't been looking for them. And now people are starting to look for them everywhere, and they're finding them. And we went looking for them at Lake Tahoe. Next slide. So here's this is much of this is too small for you to read, but I'll just point you to the important things. So the columns you see there are different lakes in the U.S. Lake Winnipeg, that's Canada, Lake Superior, at the end, Lake Tahoe. So they're all different sizes and shapes and things like that. Next slide, please. Okay, so what we're seeing there is in each of these lakes, the concentration, the abundance of microplastics. And what you see, Lake Tahoe at the end, there's more per square kilometer of Tahoe than any of these lakes. These are all big lakes. Includes Lake Superior. Lake Tahoe has as many microplastics on its surface as San Francisco Bay. Again, another one for Hawaii. I should be paid from the Hawaii Tourist Board. And this is perplexing in many ways, especially if you look at the line above the blue one there, where it says wastewater treatment. Lake Tahoe has all of its wastewater diverted. None of it enters the lake. It's sent off to out of state to Nevada, or some of it does go to California, but out of the Tahoe Basin. All these other lakes, some fraction of people's laundry water and dishwater and toilet water goes into the lakes. Yet Tahoe, despite the fact that it doesn't, has all these microplastics. Next slide. So this is just showing, I guess this is just showing the types of plastics that we've been finding. This is based literally on just a 1-year study. It was just a scoping study to see what was there. Next slide. And so there's polyethylene, and you can see the sorts of things polyethylene is in, and polypropylene and these are everyday things. These aren't things that you'll find in some chemical plant. These are in your clothes. These are what the tires on your cars are made of. It's the plastic wrap that you bring sandwiches in, when you're having a picnic on the beach. It's all there, and it's ending up in the lake. So the good news about this is, of all the problems that lakes have, Tahoe included, this is one that has the greatest potential for people to individually do something about. I mean, climate change, yeah, we can individually generate less carbon, but realistically, individually, we're not going to make that much difference. But with plastics, you can make a difference. Okay, next. Okay, shrimp. Sorry, we're all out of the shrimp special. Next slide. Okay, let me introduce you to Tahoe shrimp. This is the mysis shrimp. And so biologically, Lake Tahoe displayed greater change in 2022 than in any year since 1968, when we started monitoring monthly, year-round. And much of that seems to be centered on this guy, the mysis shrimp. So he looks really big there, or she. I can't tell the difference. But they're small, about the sort of width of your fingernail. So yeah, it's really hard getting a toothpick through them. So they were introduced. Has anybody here ever worked for California Fish and Game, Fish and Wildlife? Okay, don't take this personally. Okay. So in their infinite wisdom, which they have, both California and Nevada, there was a decision made in the 1960s to introduce the mysis shrimp to Lake Tahoe and to many other lakes across the West. And they had the reason they did it is that they were introduced to a lake in Canada, sort of a shallow lake, and the size of trout in that lake just exploded. They were huge. Anybody here fish? Enjoy fishing? Okay, so as you all know, as experts, there's nothing a fisherman likes more than to catch a bigger fish. And so those institutions were under pressure to introduce these magic shrimp that produce these giant fish. And they did it. Okay, next slide. Okay, so yeah, actually click again. Okay, now we're underwater again, not with a scuba diver. This is a sort of a remotely operated vehicle. This is about 300 feet down near the mouth of Emerald Bay. You're looking at a day in the life of mysis shrimp. So you see them just swimming around there. And you get a couple of close-ups sort of coming up there. I mean, I guess their mothers probably think they're beautiful, but they have these big eyes, and there's just lots of them there. Okay. Anyway, we could probably click to the next one. Oh, and again, no, we want to get away from them. Okay. So the reason they were such a disaster in Tahoe and many other places is related to their big eyes. They don't like light. And Lake Tahoe is very deep. So during the day, they migrate down to the depths of the lake. That last video looked light, but that was because the vehicle had lights on it. It was really very dark down there. They're down there, trout are down there, but they're sight feeders. They can't see them. So they're safe there during the day. During the night, they come up. This is a huge migration. They come up 1,000 feet and expending a lot of energy. So there has to be something in it for them to do that. What's in it is all the zooplankton that the trout normally eat. So what they did is they decimated what the trout were eating and retreated next morning. And so there was actually less food for the trout to eat. Go figure. So the average size of trout went down in Lake Tahoe. So these are data now from mysis shrimp. This is just since about 2012. We have 2 stations there, one shown in red, one shown in yellow, and you can see it fluctuates a lot. Part of the fluctuation is because, when you measure at just one site, there's lots of variability. But with those 2 sites, sometimes you see one is higher, one is lower. The thing I want to draw your attention to, click again. Okay, is in this last 18 months there, you actually see right at the end, both sites drop down very close to 0. You also see there's a blue dashed line across there. So that was a line that was determined back in the 80s when people were interested in mysis shrimp, 70s and 80s. They found that below a concentration of 27, when they were below that, these other zooplankton could coexist with them. When they got above 27, there were too many mysis shrimp and they just eat everybody, especially the Daphnia. It's a cladoceran, and it's always symbolic of good water quality. So anyway, end of 2022, the population crashed. Next slide. Okay, so this is a chronology of food web changes. This is all coming towards a conclusion now. If you're wondering when it's going to stop. Okay, so this is the average mysis concentrations over a couple of years. It's averaging the red and the yellow lines, and you see at the end there, it's down below that magic number of 27. Okay, next slide. Okay, this is a little messier. This is showing the other zooplankton that exist in the lake. And you see sort of in the first year and a half, they're sort of up and down, nothing too spectacular. The green diamonds at the bottom, they're the cladocerans, they're the Daphnia and the buzz minor. Those of you who are interested in those details, they were pretty much wiped out by the mysis, and you can see they're pretty much always at about 0. So next slide, please. And this is showing the clarity of Lake Tahoe. So it's measured with a Secchi disc, which is around 10-inch white disc that's lowered down, and we're recording how deep you can see. And it's around 65, 70 feet. Ignore that. You can ask a question about that later. But basically around this time, it starts to get a little bit clearer. This is sort of a reverse axis. The lower you go, the clearer the water is. Okay, next. So, big arrows. What are the big arrows? First big arrow, that's about the time when the mysis dropped below this critical threshold. Next big arrow, 2 big arrows. This is sort of showing this period from about June 2022, where the yellow symbols, so they're rotifers, suddenly started exploding. Actually, they exploded so much, they didn't fit on the graph. So the graph goes up to about 4,500. They're at levels of over 20,000. And I guess the second green arrow there, that's when the cladocerans, the Daphnia, start coming back. Next one. So what's remarkable here, and if we showed this going back to 1968. You'd see sort of variations like that. Right at this time in June, we start to get this pretty constant improvement. On this scale, it doesn't look that big, but I'll show it to you on a different scale in a few minutes. Next slide. Okay. So mysis died. Other things happened. Everybody, I mean, I get all excited about the clarity. The question I always get is, why did the mysis die? Everybody is like, they feel for them. I mean, you shouldn't. Really, they're not worth your emotional capital. Okay, next slide. Yeah. Okay, we have two theories, neither of which we have enough data to say is right or wrong, or both are wrong. So one of them, what we noticed in our sort of sampling of zooplankton is what the mysis usually eat. The copepods, we started noticing a lot of them were fuzzy, meaning, well, maybe they have some kind of fungal infection. That's something we're still looking into. So that hypothesis is the mysis food web, or the food source, crashed. They got some, the food source crashed, got some fungal infection, and the mysis simply starved to death. Yeah, maybe. Next one. Okay, this one may be a little bit more out there. I don't know if I believe it, but it's sort of the timing is right. So August 2021 was the Caldor fire. So I mean, most of the Caldor fire was away from Tahoe. A little bit came into the south, the sort of upper part of the South Shore, but there was smoke. There's an incredible amount of smoke for weeks and weeks at a time. Air quality indexes of, I mean, meaningless, 500, 600. It was, and smoke deposits, it's particulates. They deposit on the lake. What we noticed right after this were very large abundances of a cyanobacterial alga known as leptolingbia. So cyanobacteria have the potential to be toxic. Repeat that, have the potential to be toxic. We didn't take samples, we didn't measure the toxicity, but for the first time ever, we saw huge numbers of leptolingbia. They were the dominant alga at that time. And we know from lab studies that they like the conditions of high ammonium associated with wildfire smoke. So it's pretty clear they were there because of the fire. Did they have a role in the demise of the mysis? We don't know, but that's as close as I can get to answering the question, why did they die? Next slide, please. Oh, okay. Just quickly, there are lots of, these are the main biological changes, but there are other things happening too. Large algae are coming back. Next slide. I need to wrap this up. Okay, this is, okay, very quickly. Okay, this is going back to 1968. This is showing biovolume. This is basically a measure of the size of algae. And way back in the good old days when you could see down 100 feet, there was high biovolume, which doesn't mean lots of algae. It means big algae. And then over this whole time when clarity was decreasing, biovolume decreased. Lots and lots of smaller algae. And suddenly, in the last year or two, biovolume has shot up. Next slide. This is a graph of primary production. So this is different. This isn't like a concentration of anything. This is the rate at which photosynthesis is happening. So it's been going up steadily at Lake Tahoe, again, since 1968. But the last 2 years, it's been really high. Next slide. Okay, this is where we do the wrap up. What's this? What has this got to do with clarity? Okay, so this is the chart of clarity. Secchi depth for Lake Tahoe. Each of those circles represents the annual average of about 25 readings. You can see going back here, it was decreasing. But again, decreasing means going up. The closer to the surface, the lower the clarity. So it was at its worst, let's say, in about 1995 or 6. And then it's flattened out. So coincidental with this expenditure of hundreds of millions, billions of dollars, the decline stopped. Maybe a coincidence, but maybe all these efforts at least stopped the decline. And it's been flat ever since. So this last year, 2022, the very last dot there, you look at that, it doesn't look abnormal. That's below the line, but not that far below. But next slide. So what I'm showing here, all those light blue dots, are all the individual measurements for the last 20 years. And you can sort of see, well, clarity is generally highest early in the year. It decreases in the middle of the year, and then it goes down. 2022, the dark blue dots started off looking like a typical bad year. And then suddenly around June, it changed trajectory. It cut right across everything we'd experienced in the last 20 years and went to some of the best clarity. Next slide. We can put this in a different way. If we average the clarity for the period August to December, that's when I said things were better. And we compare that with the August to December clarity of the entire record, all the way back to 1968. So that red dashed line is sort of going through what we saw in 2022. If you project it back, we haven't seen conditions like that since the 80s. I mean, you're all too young to know what the 80s were like, but I know. So that's the big story, is that, well, several big stories. So there's been lots of money spent, lots of great effort, lots of good intentions, lots of great engineering, trying to stop contaminants getting into Lake Tahoe, to stop the decline in clarity. And yeah, at best, they've stopped the decline in clarity. They haven't improved it. And the improvements have been incremental. Yet in 1 year, there was this huge change because of a change in the food web. As an engineer, it's really hard to say the ecologists were right. Yeah, it is. It hurts. But it seems that there is something to it. Now, and this is the sad part about it, is, as most of you know, all the attention to Tahoe and the loss of clarity has always been pinned on all the development that happened starting in the 60s. And that's true. It happened and it caused lots of bad things. The mice and shrimp were introduced at the exact same time. And I would conjecture that both of these things were impacting the clarity. It's just that the development and that whole battle, keep Tahoe blue, is what was capturing people's imagination. And that was happening all over the world. Too much development causing decline in coastlines and lakes and rivers everywhere. So that theory, that line of action, was not sort of weird. It was what you should be doing. Okay, next slide. So Lake Tahoe is changing like never before, yet too many of the I'm gonna skip to the very end because I told Tom this would be 30 minutes, so don't worry. Keep going. Okay. Is it the end of Lake Tahoe as we know it? I love this. It's at the Met. It's great. I don't think so, but it's changing along with the rest of the built and natural environment. So that Lake Tahoe isn't necessarily an outlier. But there are many reasons to be optimistic, to think that it's just going to get worse and worse. And I think a lot of it has to do with the increased understanding we're getting. Those slides we just passed by were all about this real-time system and autonomous vehicles we have that are giving us data like we've never had before. And so with that data, with the knowledge, I think we're at the point where good things can start to happen. I mean, how do you capture? I mean, can you control mysis shrimp? It's a good question. So I think I'll leave it there. I think on a positive note, most talks that invoke climate change are never uplifting. But that's it. Next slide. Thank you very much. Oh, that's too far. Okay. Yeah. Yeah.
Okay, is that done now? Okay, I understand Key West was built on the watershed, and it looks like where you're having problems around that part of Tahoe, you're having more problems there than other places.
Yeah. So yeah, you mean Tahoe Keys?
Or Tahoe Keys. Oh, I said Key West. Tahoe Keys. Excuse me.
No,
I'm in the wrong state.
Okay. So the question is, is it a coincidence that most of the problems, that there are many problems around the Tahoe Keys at the south end of Lake Tahoe? Well, there's probably good reason to expect that to be the worst. I mean, the Keys themselves have huge problems. So if you're not familiar with it, this was a concept of Venice in the Sierra, very popular in the 1960s. So you take the largest river that flows, largest stream that flows into Lake Tahoe, you divert it around the largest wetland in the Sierra, you dredge out that wetland to create channels and give everybody a dock. And so that's like they're in Venice in the Sierra. Yeah. I mean, a lot of the problems are there because that wetland was there capturing nutrients and fine particles from that large inflow. And the Keys have their own problem. A lot of it also has to do with the fact that because of the sediment over the centuries, thousands of years coming in, there's a very broad shelf at Lake Tahoe. So that's really shallow water. It gets warm. And when we have a drought year or several drought years, it gets even shallower. So I think that's what's happening. I mean, putting aside the Keys themselves, is that South Shore, because of its shallowness, a lot of nutrients get trapped there. The warm water enables the algae to grow, and they wash up on the beaches.
I have so many questions because I took my class on the history of Lake Tahoe up to your research center. Okay. The other question I have is about these little shrimp, because when we were up there, and it's been about 3 years ago, it was right before COVID, I think, when we came up, and they were talking about, and they were saying the shrimp come up at night, and that the college students were actually going out and scoop, they had some nets and they were picking up a lot of these to try to see if they could, although there were billions of them, to try to see if that would help. Is that still going on, or is that just given up on that, or what?
Well, those college students referred to are fine employees of the University of California. But many of them were college students in the past. Yeah. So this is a neat opportunity. And this is very controversial. And I'm a believer. And there are a lot of people believe along with me, and there are many skeptics as well. So when the shrimp come up at night, they come up from deep down, and they come up to about, say, 60, 80 feet below the surface, and they form a band there. I mean, they just like that depth. So if you look at it through an echo sounder on your boat, you see this thick band. Okay, an echo sounder on on a boat, also called a fish finder, tells fishermen where there's fish. This is telling us where there's shrimp. And so the idea was, why don't we get a really big net and troll for them? And when we did that, we could catch them. Okay, now the exciting part. So we thought it still costs money to go out every night and troll. This was all happening in Emerald Bay. Tahoe is just way, way bigger. So we went to the Graduate School of Management at UC Davis, and they were looking for projects. So I said, hey guys and gals, we want to commercialize the harvesting of mysis. What do you think? So we got this great group. They were fantastic. And they looked at a whole range of things, got lots of analyses done. Okay, these are the results. Number one, mysis shrimp have double the omega-3 fatty acids that salmon have. So they're detestable and ugly and all those things, but they're really good for you. High in omega-3, low in everything else, no contaminants, nothing. So trying to get them licensed for human food, well, there's lots of hassles with that. And the idea was, well, what about dogs, pets? And so, a long story short, they've developed dog treats. Come on. And nobody please say, oh, Lake Tahoe's gone to the dogs. We've heard that one. But they ran a whole financial analysis, and after a $2 or $3 million investment, well, it's a lot of money. And remember, they're currently spending $20 to $30 million on things that aren't working terribly well. It becomes self-sufficient as long as you have 8 or 10 troll boats willing to work 4 months a year, from August through December. So it's doable. So we are pursuing this, but we need to get a permit from California Fish and Wildlife to prove, first to get that permit, we have to prove there's no bycatch, that we don't catch any fish at the same time. But because the mysis have been down the last couple of years, we haven't been pursuing that, but we're about to start that again. So it may be that it's a sort of a double approach. You keep doing all the things in the watershed, in the basin, reduce sediments and nutrients coming in, but you also start reducing the mysis shrimp and allowing things like the Daphnia to return and possibly get these same large increases in clarity that we've seen. So.
Another question? One more?
Fish and game are back.
I'm not, I'm used to the bad treatment of fish and game people, so I'm not going to make any comments on that. I just wondered, I don't know if you're working on the nutrient cycle in the lake. What is going on with the nutrients? Because that would be the basis of the whole change in water clarity. The whole food chain depends on that. What is, in general, what's going on with the nutrients?
Well, I mean, that's one of the fortes of the UC Davis lab up there, is that it's specialized in low-level nutrient chemistry, because these are the levels of Tahoe are, like the middle of the ocean. They've stayed remarkably consistent, despite, all the changes in the lake in the last half century. So that's not changing a lot. And maybe it's because nutrients are being taken up by algae and then they settle out. So the background concentration stays the same. There's a lot we don't know about recycling. There's a lot we don't know about the really tiny algae, the picoplankton. That people don't know about that in lakes. But the one thing that has happened is, I kind of alluded to it before, is there has been a change in algal size from 100 microns down to 2 and 3 microns. And so it's not so much the nutrients that are affecting clarity, it turns out. It's very fine particles, something in the sort of the 2 to 7 or 8 microns. So the thickness of your hair, well, Tom, you wouldn't know about this, is about 100 microns. So these are tiny, tiny algae, and they scatter light. So those tiny, tiny particles, they scatter light. We used to think it was just clay, but we've since learned that it's the algae. And so nutrients affect those tiny algae, but we're still trying to sort through all of that. But that is the central Tahoe issue, clarity.
For a great presentation.